All right, so we talked about plane mirrors that give us a virtual image that is upright and is the same size as the object and is the same distance behind the mirror as the object in front of the mirror, right? And the fact that it's behind the mirror, that's what makes it virtual. There is no light back there, but the extension of some light. So you can go back to the drawing of the plane mirrors and you can see what I'm talking about. Now we're going to have a mirror that's kind of curved. And I'm just going to do this with the concave mirror first, and then I'll do convex mirror. So a concave mirror is where the reflective side is on the inside. Okay? So now, the way we do this, the way we draw the image of this object, so this arrow here is the object. So anything that's coming from infinity, basically, that's coming parallel to this principal axis here, okay, will reflect through this point here called the focal point, right? So every curved mirror or curved lens has a focal point. Okay, so that's my reflection. And I'm going to keep an eye on this reflection because in order to get images in mirrors, you have to follow where the reflections intersect. Now, the C is the center of the curvature of this mirror, and the distance from the mirror here to C is 2 times the distance from the mirror to the focal point here. Now, the other one we're going to do is anything that goes through the focal point will come back parallel. So if I go, I'll do this in a different color. So if I go towards the focal point, okay, hit the focal point, hit the mirror, right? And that's the incident ray, and then you're going to come out parallel to the axis of principal axis, okay, or the optical axis. So that's about parallelish. Okay. And your image will always be the intersection of your reflections. So I can see that my two lines intersect here. Okay, so what I found is just the image of that tip over there. So I can see here that the image is real because it's happening what it's supposed to be happening. So mirrors reflect light, so you expect your image to be on the same side as the object. If the image happens to be behind the mirror where it's not supposed to be, that's a virtual image. The other way you can look at it is these 2 rays of light are real. They are not the extension. They are not the extensions of real rays of light. So this is a real image. And I gave you a shortcut before that if it's real, it's going to be always inverted. And if it's virtual, it's always upright. So that's just a shortcut. Now, we could have done this in an infinite number of possibilities. Another one will have been, if I come towards this intersection point, okay, at an angle, I will bounce back with the same angle. Okay? So if I do this, okay, if I connect that, and if I measure that angle, I come back out with the same angle, I should be passing through this point here. Okay, and the reason for that is because we're just following the law of reflection. The curvature of the mirror here, okay, at that point, if I draw the tangent there, is perpendicular to the principal axis. That's why. So we're following the law of reflection. Another way you could do this is anything that's going towards the, that's going through the center, maybe I'll draw this one and I erase it. Anything that goes through the center will reflect back on itself. And the reason for that, okay, because this is kind of like the radius, and it's perpendicular to the tangent to the mirror here. So you're hitting the mirror at an angle of 0 degrees, you're going to bounce back at an angle of 0 degrees. So you go at 0, you bounce back at 0. Okay. So I'm going to erase this. There's no need for it. So I'm just going to stick with this 2 ideas, parallel focal point, parallel. But feel free to go through the center and bounce back the same way.
Probably. We're all in here.
Okay. So let me see, I host where point C is.
Go.
Point C is here. Okay, so a couple things that I have here. So I said if I go parallel, I come back to the focal point. If I go through the focal point, I come out parallel. If you go through C, you bounce back on C. And if you go with an angle here in this part here, you bounce back with the same angle. Okay. Now, this is what we call a converging mirror because it takes the rays of light and it brings them together. So this is a converging mirror. Okay, and it's also called a concave mirror. Now, if it's a convergent mirror or a lens, we'll learn that later, the focal distance is positive. This F here, this distance between the mirror and F is called the focal length, focal distance. That's F, that F is positive. Okay, if the image happens to be back here in the wrong place, okay, then the DI will be negative because it's not supposed to be back there. Okay, and the image will be virtual and it will be upright. So let me just write that down. Okay, so a virtual image means that it's not going to happen on this side, so it's going to happen behind the mirror. So basically, I can say the wrong side, okay? And it's going to be upright, so it's upright. And the distance between the image and the mirror is going to be negative because it happens to be on the wrong side. So pretty much we're looking at everything that happens to the left here as positive because that's where the thing's supposed to happen. Anything that's happening in the wrong place, the DI is negative. And the magnification of this, meaning like the size of the image compared to the size of the object, is always going to be positive. Because this image will be upright, so which means the height of the image over the height of the object will be a positive number because they both pointing in the same direction. If the image is real, it means it has to happen on the left side. So that's the right side. So same side as the object. So same side as object. And it's going to be flipped, which means, I'll do this in order. It's going to be flipped, so which means it's going to be inverted. Okay? And the DI is in the right place. So it's supposed to be on this side. That's where the light is reflected. So the DI will be positive, but the magnification would be negative. Because if it's a real image, it's going to be flipped compared to the object. Okay. And I think that's pretty much it. Now, so in class, what we're going to do, we're going to put this object at different locations. And we're going to make the image. And you're going to see that the image will change shape or location based on where you put your object. All right, so I'm going to do a convex mirror here. A convex mirror is a diverging mirror. So convex, also known as divergent. It has a F focal length that's negative. And I'll show you the equation with this focal length here. Okay, so it looks something like this. So that's the non-reflective side. Yeah. So, and this is the principal axis here. So I'm going to put an object here. Okay. And the focal point is on this side. That's what makes the focal distance negative because it's on the wrong side, kind of. Okay. So now, how do we do this? Okay. So this is F. I guess I can say that this is C. All right. So I come parallel here, but I'm not going to go through the focal point because light cannot penetrate the mirror and go to the other side. It's going to reflect. But here's the trick. It's going to reflect as if it's coming from this focal point. So it's going to reflect this way. And that's the diverging property of the light. See, you came in with a small angle, now you just went wide. The other way we can do this is, the other way is if I go towards the focal point, but I cannot reach it because the mirror is in the way. So if I go towards it, okay, as if I'm going at it, I come out kind of parallel. Okay? See, the light cannot get to the other side. That's why I do dotted lines and not solid lines behind the mirror. Okay? Now I have to follow these reflections and see what they meet. So here's a reflection, here's the other reflection. And I hope you can see that the angle is wider, right? People have these kind of mirrors at the end of their driveways if they live on a main road, because when they're backing up, they can see basically all of the main road. So it gives them a big view. You have them also on the side mirrors of your car. Okay, so the image is going to be where these two lines intersect. So we have to figure out where they intersect. Well, if I extend this line, and if I extend this red line, that's where they're going to meet. Because they're not going to meet here. And they are not parallel, so they have to meet somewhere else. You meet there. So for the convex or a divergent mirror, you're always going to get, no matter where you put the object, you're always going to get an upright image. So the image is going to have these properties here. It's going to be upright. It's going to be virtual. And I hope you can see why it's virtual. Because it's always going to be created on the wrong side. The other way you can look at it is you can see that the point of intersection is just the extensions of true rays of light. And it's going to be the DI is in the wrong place. Okay, DI is negative. Magnification is positive because it's right side up, right? So it's upright. And what else? It's going to be smaller, which means the magnification would be greater than 0 but less than 1. It's always going to give you a smaller image. Okay? Now we're going to do, okay, I'm going to make another video, and that's going to show you the lens formula, basically, the proof to the lens formula. And everything I've done here, just in case I don't do another video for lenses, it's pretty much the same concept. Okay, the same rules apply to lenses. Okay, all right, see you later.